Your brain is firing electricity right now, and some computers are already learning to listen. Every thought you have starts with neurons talking to each other using tiny electrical pulses. These pulses are real, measurable signals, and that means, in theory, a machine can pick them up. A brain-computer interface, or BCI, is a system that reads those electrical signals and turns them into something a computer can act on. The basic pipeline has 3 steps: record, decode, and command. The first challenge is just getting close enough to the signal. Neurons are small, they fire fast, and the skull muffles everything. So researchers have 2 broad options: sensors on the outside of the head, or sensors placed inside. EEG, the kind you might have seen in a hospital, uses electrodes on the scalp to pick up the combined electrical activity of millions of neurons at once. It is non-invasive and safe, but the signal is blurry, like trying to hear one conversation in a crowded stadium from outside the building. Implanted electrodes sit directly on or inside the brain tissue, which gives a much cleaner signal. You can actually track individual neurons firing. The trade-off is obvious. It requires surgery, and that carries real risks. Once you have a signal, raw electrical data looks like messy, squiggly lines. The next job is filtering out noise, things like muscle movement, eye blinks, or interference from nearby electronics, all of which can look similar to brain activity. After cleaning the signal, the system looks for patterns. Different mental states and different intended movements produce different patterns of activity across the brain. Researchers map which patterns match which intentions. This is where machine learning comes in. A model is trained on recordings from a specific person, learning to recognize their unique neural fingerprints for things like imagining moving a hand or focusing on a particular letter. When the person thinks about moving their hand, the model spots that pattern and sends a matching digital instruction, maybe moving a cursor left, or triggering a robotic arm. The brain did not move anything directly. The software made the translation. Speed matters here. For a BCI to feel natural, the delay between thought and action needs to be very short. Current research systems vary a lot on this, and it is still an active area of work. One honest limitation is that these systems are usually trained on one person and do not transfer perfectly to someone else. Brains are individually different, the same way handwriting is. Most BCIs in clinical use today help people who have lost motor function, letting them control a computer or communicate when they otherwise could not. That is the clearest practical application right now. The core idea is straightforward even if the engineering is hard. Electricity in, pattern recognized, digital command out. Everything else is just solving the problems in between. If you want to understand what the current research is actually trying to solve next, the question of long-term signal stability is a good place to start looking.